Ага, we'll start the training.
Hello, good afternoon, everybody. I think we can start. We still expect some more people, but they will join later, hopefully. So, yeah, I hope you can hear me, and I think we can start day 2 of this DFT training. So yesterday we went through the overview of the tool. We talked about a lot about the workflow. What are the main parts of this workflow? And we had some slides about the issues and some best practices, and I showed you some formatting and content issues related to the input files, and also you saw 2 reports which we use during this data collection. So today we try to go a bit deeper and talk about at first the different types of models, still on an intuitive level, but to shed light on some details that may be interesting for you as a user. And also we talk about the different components which we add to our forecast to adjust it. And they are based on the technologies we expect will have an effect on the electric load. These are heat pumps, AC, EV, batteries, PVs, and then we will have some thoughts about some, we call them advanced modeling features, but they are simply just target demand rescaling and peak adjustment. So, and of course, in the end, and during the presentation, feel free to ask questions if anything is unclear. And I think we will have lots of time in the end if you have many questions. So yeah, let's do it. So I wanted to show you again this overview of the tool. So it has it has 2 main parts. There's a data-driven model, which tries to create a baseline forecast based on this statistical relationship between the load and some independent variables. And there is this adjustment of the forecast based on the technologies we think that are important. And the 2 of these make up the total forecast of the DFT. And this methodology is really similar to the previous one, which was in Trapunta. But right now we have this user interface, and we have this online tool, and we have this possibility to create projects, save them, and iterate on our expectations and assumptions. So what are the statistical models? We talked about them already a bit. So we can select in the DFT 3 types, basically. One is a linear regression, the other 2 is random forest and the GAM, which is generalized additive models. We may know a bit more linear regression, so it's not the models are linear, but the parameters are linear, and so they can kind of so a simple association between the variables can be estimated with them. Sometimes they are very useful, but for other times when nonlinear and models with many parameters are needed, maybe a more flexible model is better. And random forest and GAM are both really flexible and powerful models. And yeah, they have a history of giving good forecasts for different types of problems. So a bit more, but still on the intuitive level about random forest and GAM. So they are kind of non-parametric models, and they can explore different nonlinear relationships between the explained variable and the explanatory variables. And of course, yeah, it's common between all of the methods that their algorithm aims to minimize the errors between between the forecasted or predicted values and the observed values. You can see on the in the bottom on the left hand side a visual intuition of the GAM, how it composes the final prediction for a given function. And on the right hand side, you see a visual intuition about the random forest, which is kind of a complex decision tree model. And yeah, both of them they are quite different in their construction. So that's why they can be kind of good alternatives for each other. So in one certain case, maybe one is better than the other. So that's why the developers, that's the one of the reasons why the developers chose these two a bit distinct types of models to include in DFT. A bit more about the GAM. So it originates from a simple linear regression, but instead of fixed weights for every feature, it introduces a smooth function of these features, and the GAM methodology adds them up. So the methodology still thinks or assumes that they are independent, these components, but they are not just simply um, multiplied by a weight, a parameter, but so it introduces a smooth function for them. And especially in DFT, the smooth functions are so-called cubic splines. So the final prediction will be this kind of sum of weighted cubic splines of the different explanatory variables. So once again, in the bottom, you see this intuitive picture. So on the left-hand side, this is one function, one smooth function. And on the right-hand side, on the small graph, you can see how it creates or assumes lots of these smooth functions for a given x variable and how it adds up them together to get the final prediction for the dependent variable. Two important hyperparameters exist, or we care about two hyperparameters for GAMs. One is the so-called lambda, and the other is the number of splines. So lambda is a penalty parameter for every kind of smooth function. And the number of splines is just how many of these smooth functions should be used for a single dependent explanatory variable. And both of them tries to control this overfitting or flexibility, which we talked about previously. And yeah, both of them from a bit different perspective, but tries to do the same a bit different way. So on the right hand side on the top, you see the four cases when to the same data points for different types of parameterization is fitted. And then this way you see intuitively a bit how these parameters affect the estimation. So yeah, if we go from the left bottom picture, we see that there is low number of splines for this given independent variable, and there is a high lambda. So it's really a restricted function what we impose here. So that's why there's a straight line still only. And if we go to the top right of this graph, you see that we have then the opposite case when we have high splines and low lambda, so low penalty. And then we see that the prediction is really flexible, or the function is really flexible, and the prediction is really wiggly, as we call it. So on this way, maybe it's a bit too much, and for these data points, and this is when maybe overfitting takes place. So in DFT, it's important that the developers decided to fix lambda for every model and for every market node inside the GAM. And the user can only choose the number of splines for each relevant explanatory variable. So yeah, they try to find a lambda which is not too restrictive, but also not too flexible. So in the middle, and then we are free to choose the number of splines in order to balance this overfitting. I think for this GAM, I just show you the interface again, because if somebody has not seen it, then maybe it's better to show what's going on. So we have this previous example when I just started the project and I imported the data, and I can go to the modeling, and then okay, so now I create a new task for my data. I choose the training period and the test period and click on validate, and then now I can create a new model for this market node. And I want to
Can
right
you
now
please
just
share the?
sorry. Thank you. Of course, I was just sharing this window. Okay, so so I was like here in the data-driven modeling section of the tool, and I clicked on new task because it was a previous project which I already created and made a model on, but I now create a new task, and then I select the training period and the test period. It can be this one for the time being, and I click on new model, and then I can select my previous models, and also I can create a new model from scratch. This is what I would like to do now. And then just to show you this GAM interface, I will, and the hyperparameters that we can select, I will just, yeah, come here, and then you can see that this is the thing which we can choose for a GAM model as advanced parameters. And the lambdas are not there. The lambdas are fixed inside the tool. This was decided by the developers. So this was I was talking about. I will talk about these other things a bit later or soon. So, okay, it's easier to have the whole screen. You can see it now. And then, yeah, so basically this is the GAN model in DFT. Let's turn to the random forest model. Still, it will be really high level and just to build up intuition. So the random forest originates from decision tree models, and basically this right hand side, on the right hand side, you see how the algorithm works. So it just selects a sample of the training data and then create for this sample a decision tree. And then it will do the same for many times, as much time as we want. And then after doing this and creating a single prediction for every decision tree in the end, it will vote, and it's so-called vote and average all these predictions together to have the final prediction. So, so actually, yeah, it's a bit of a black box in this way, because there are many models which are fit and then they are aggregated in the end. But this way, it's a really flexible model, and it can estimate complex relationships between variables. So what we need to know is that in DFT we can adjust the number of trees or estimators parameter and the maximum depths of parameter of the random forest. And what this means is the number of trees is the number of decision trees, basically, that are being estimated, and the maximum depths is the depths of, or the complexity of each decision tree, the maximum complexity of each decision tree inside one of these kind of estimators. So this way, yeah, it's again two parameters, and both of these parameters can like, you know, if they are the higher they are, the more complex the model will be. And of course, the more complexity, the more flexibility, and then this model or our model may in the end overfit. But there is a balance between, of course, these parameters, so it's not necessarily overfitting, but it can happen. So yeah, that's it. So in DFT, we have this slide here, so I don't have to change really to the interface, but I will actually. So in DFT for a random forest, if I choose random forest, then I have these hyperparameters to adjust the number of estimators and the maximum depths of a tree inside an estimator. So yeah, basically from a high level perspective, these are the two model types. Yeah, we have some more notes here. So if we talk about a GAM, we can tweak the number of splines for each regressor, but we have some regressors which are not in this, which we cannot do this. This is the hour and the months regressors. Actually, to be honest, I don't know the reason for this. Maybe these are not really like continuous variables, and then maybe this is the reason, but I'm not sure. But for the others, like as you can see in the picture, for wind speed, for irradiance, for temperature, or for these seasonal calendar variables like day of the year, you can still select the number of splines. And you can see these numbers in brackets after the number of splines. So of course, you are not allowed to provide any number, but you have to provide a number between these two values. And this is also true for the random forest parameters as well. So yeah, the random forest has these parameters, and then yeah, this is just a message to be aware of the consequence of maybe putting a high number into this for these parameters. So once again, one more message about overfitting. So this is also visual intuition. So if you like estimate a really flexible model, it can follow your data points kind of precisely, but then after some point it will not follow, but it will overfit those points, and maybe this is not what you want. So on the right hand side, you estimate a really flexible model, but this is not the thing we would like to see here. So let's talk about this model per hour option. You could see it in the tool, in the interface right here. And this model per hour is only available for linear regression and the GAM, and not the random forest. What is it? The model per hour means that we have the option to fit not only one model for the time series we have, but 24 different models for each of the different hour of the day. So if we select this model per hour option, then DFT will estimate 24 different models for each of the hour of the days. And in this way, these are 24 separate models that are estimated separately. Whereas if you don't turn on this option, but you leave it like that or unselected, then the model, the linear regression or the GAM will take all of the samples, all of the hours of the day, treat them as a single time series, and then estimate only one model for them. So this is an explicit option to select by the user. One thing to note here that we also have an hour, so-called hour explanatory variable, which is only available when we don't have this model per hour option turned on. So if we take, we don't select this model per hour option, so we have one model for all the data we have, then we still can select this hour variable to include it in the model. And then this way, for every different hour of the day, we will have different kind of, so every hour of the day will have a different kind of load, which or level of load or average level of load that the model will estimate. So in this way, we can still distinguish between the hour of the day kind of models, but it's not separate models, but these are just parameters which are different. So this theoretically both options produce similar results, but there is one technical advantage of selecting this hour of what is called model per hour option, namely that after fitting the model in the results section, if we selected this option, then we can see the partial dependence plots independently for every hour of the day. So it helps maybe to to assess the effect of the different explanatory variables, such as temperature on load in different hours of the day. And also, if we select this option, then we have 24 models, so it's not just one model. And then in this way, the predictions for the training sample tend to be more precise. But of course, this is not really what we want. We want to have good forecasting performance, and we don't want to only precisely predict the training samples, the historical load. So maybe this is not a real advantage. This is just yeah. I'm just saying that we should be aware of this as well. So, but the developers suggest using this hourly model. So to select this model per hour option, because they had some tests and yeah, they agree. They told us that it will have a more precise estimation. But once again, this is not automatically true, and especially it's not automatically true for the forecast. So yeah, this is about the different statistical models that we can choose in the data-driven modeling section. If you have any questions regarding these, feel free to ask.
Yes, I have a question, but concerning like beforehand the random tree model, I was wondering because for the other model you showed how the parameters affect the results. Is there also like a connection between the number of estimates and the maximum depth between the like if you set a high value or low value for the outcome?
Yeah, we didn't find a good like intuitive graph for that, but yeah, in principle, the more the number of trees and the more the maximum depths, the model will be more complex, and then the model will be more kind of flexible. But I don't say that it's automatically true. And as you see, there is an averaging in the end. So if you average more values, so this means that you have more estimators, then maybe this is not in the direction of overfitting, but maybe this creates a better kind of model in the end, or prediction in the end. So I wouldn't be that confident in terms of the more estimators. But the more depths is, I'm kind of confident that this is like the decision tree in each estimator is more complex if we leave it, or if we give a higher number for that. And this way, I'm quite sure that this will result in a more flexible model, and then this is analogous to the previous section where we saw that these parameters allow, if they are higher, they allow a more wiggly function. So maximum depth is more like that, but the number of estimators is, I'm not quite sure. I'm not really an expert in random forests, but at least what I can say is that the more number of estimators and the more maximum depths, the more time it will take the model to fit. Of course, because more models actually to fit, and then yeah, at least this is what I can tell, that it will be slower a bit. But I think maximum depth is definitely towards the direction of more complex model, and then yeah. Okay, yeah, welcome. And the default values for those are 20 and 8, if I'm not mistaken. So I don't know. So I don't really have good suggestions. I don't really have much experience with these random forests. I tend to use GAMS. So yeah. Yeah. Any other question maybe? So I'm just going to run this test model just in the background. It will run, and then if it finishes, I can show you the. No, okay, I didn't. I wanted to select this model per hour just to show you what you can see in the results. But it's kind of obvious that you can select both the explanatory variable and also the hour of the day if you select this option, and then you have kind of a visual interpretation of the relationship between them for a given hour of the day. So this is the only thing I wanted to show you, but yeah. Okay, so we can go on to the next topic. So it will be the different demand components that we add to our baseline forecast. So the first one is heat pumps. This training is not about the PMDB file, but you can ask questions about the PMDB file. Of course, if you are not really confident how to fill those values in and what kind of values you should use there. So, but for today, we didn't really didn't want to talk about that, but instead wanted to talk about kind of how the tool treats these components. But feel free to ask questions about the PMDB file as well. So just to show a quick overview of the heat pump model in general. So how it is implemented in DFT. So the first thing to note here is that the heat pump model and also the other demand component models are physics aware. So we call them physics aware, and it's really important that they are deterministic. So we have kind of, or DFT has built-in formulas that you can calculate the heat pump or the electric vehicle component directly. So how this algorithm was created by the developers for heat pumps. So on the right hand side, you can see that basically the electric load for a heat pump is composed of the hourly, so-called hourly heat demand and the COP, this coefficient of performance, if I'm not mistaken. So we divide the hourly heat demand by this COP, and then we get the electric load for a heat pump. And how we get there. So the developers, like beforehand, for every market node, created or generated this hourly heat demand and also the COP values in order to have the electric load for a heat pump in the tool. How this was created, the hourly heat demand is a bit more, but yeah, both of them are not that difficult, but the hourly heat demand was a bit more, I don't know, involved. So they introduced, or they used the concept of degree day, the so-called degree days, heating degree days and cooling degree days. And they also used a public database called Vent2Heat, from which they could get the daily consumption, daily heating demand for a household for historical years. And they combined these two. So they created a relationship between the historical degree days and this daily historical consumption in this database. They did it with a linear regression for heating and cooling, and then they had uh, they estimated this linear regression, and they got some parameters for every country, different parameters for every country, for every market node. And then with these parameters saved in the tool, and they are fixed, they can forecast the daily heat demand to the future by using not historical degree days, but future degree days from the PCD data. So, and then this daily heat demand is modulated by PMDB profiles, which are the inputs from the user or from the LUC or the SUC. And there is also one other modulation based on the temperature. And then this is how they get the hourly heat demand in the end. I hope it was clear from a high level perspective that there was some initial analysis by the developers, and they saved some parameters for every market node, and they use these parameters to create future or to get future heat demands for every type of heat pump. It can be heating, cooling, and also these so-called sanitary water, like heat pumps or demand. So this is true for every type of heat pump, basically. This methodology, and yeah, we have this COP formula. This is also something which needed a bit of pre-analysis by the developers. So they, based on the temperature difference between the ambient temperature and the so-called sink temperature, or the source temperature and the sink temperature, so the temperature difference that the heat pump should like overcome. So based on that, they estimated or used the functional relationship between this different temperature difference and the COP, and then this way they are able to like have an estimation about the COP in an hourly basis for every type of heat pump, and then they can use it for this electric load estimation. I hope it was not very confusing how I said this. So this is the overview of the methodology, and yeah, we have this PMDB file where we have to provide numbers. We have to provide values for these heat pumps, and yeah, so we only wanted to just tell you some notes and cautious messages that yeah, please carefully fill in these data. Yeah, please note that these units are additional units, but you can also provide the target demand for heat pumps for different types, but they are not additional values, but they are like nominal values, so accumulative values. So please be aware of this difference. And yeah, as I said, if you have any questions about these values, you can ask them. And also, I hope you will have access to the online documentation where you will find the data collection guidelines as well. So I hope it will also help you like fill in these databases. Once more, or yeah, additionally, there is another sheet, or there are other sheets which are related to heat pumps. These are these heating profiles, cooling profiles, and water heating profiles. It's really important that you are aware that the defaults are flat. So these profiles are flat in PMDB by default. And ENTSO-E doesn't really want to give any different profiles for them as a default. So please make sure that if you have some information about, or if you would like to adjust your heat pump evolution or modulation, then this is a place where you can do it, because these daily profiles are kind of, they have a strong impact on the heat pump demand. It's quite flexible in the tool, so you can select, or you can provide lots of types of these profiles for every month and for every week or day type. So I know it's a bit overwhelming, it can be, but yeah, if you would like to see some not flat evolution for a specific day type, then this is the place where you can do it. This is also, yeah, explained, I hope, clearly in the documentation. One other thing, there are some countries which the developers didn't have data from this vent to heat database. So to overcome this problem, they used other market nodes data, and they estimated the parameters for the heat pump demand based on like the neighbors of these countries. So for these countries, it can be, I don't know. So it's hopefully they work for you as well, for these countries as well. But just to, yeah, make sure you know about this difference, that there were some countries which were not present in this database. So that's why the developers had to do something. Okay, and we have kind of a bit more detailed slide about how the computation of the COP and the computation of the heat demand is carried out. So, sorry, up here on the slide, you see the basic equation that the DFT uses to get the electric load related to heat pumps. So it's the heat demand or the cooling demand divided by the COP. And the way this heat demand and COP is calculated, I talked about earlier. So for heat demand or cooling demand, they created this regression, which you see on the top here. They created this regression based on historical data. So it's a regression between the heating degree days and the daily heat demand from this vent to heat database. And then with this regression, or with these parameters that they estimated previously, they are able to create forecasts for the daily consumption of these heat pumps. So they use the same parameters, A and B, but they use, or they calculate the heating degree days or the cooling degree days based on the PCD values for the future. So this is the basic kind of assumption. And then this daily consumption is modulated by this PMDB profile that the user provides. And also there is a so-called, we call it profile twisting, additional profile twisting based on the PCD, hourly PCD temperature. Also, I didn't mention that, but there is a data point in the PMDB where you can provide the efficiency, the yearly efficiency evolution of your buildings, I think. And this is also taken into account for the final demand, final hourly demand. So the more the efficiency, the less demand will come, or the less the demand will be. Yeah, basically this is the methodology behind the heat pumps. In the online documentation, there is even more. There are even more details. In the documentation, you will find. Yeah, I can show you actually. Even if you don't have the access. I hope I have the access. So in that documentation, you have the basis here on the left-hand side, and then you have annexes and no, it's not in the annexes. It's the forecasting, technological forecasting heat pumps. And then for these heat pumps, you basically see this, the basic assumptions and equations and this overview as well. And then you can go through a bit more detailed explanation about how the daily heat demand was computed or is computed, and how the COP is computed. So yeah, here they have a more explanation. They also explain the cooling demand as well, which has the same logic behind, but of course it's a bit different. And also the sanitary water demand, and also this missing market nodes, how they treated them. And some other hyperparameters are explained, how they estimated it for each market node. Also, you can see here how the COP time series is obtained. So they assume for every type of heat pump, they assume this kind of functional relationship. It's quite a basic. I forgot. Okay, it's a kind of basic non-linear assumption, and then they explain a bit more about the temperature difference, how they treat them for a given type of heat pump, and then they also explain this technological efficiency, which I talked about. It's also the building efficiency and also the COP. In the PMDB we can even provide the COP evolution. But it's just the trend of this evolution which is needed for the DFT, because it calculates itself the time series, the hourly time series of the COPs. So that's it about the heat pumps. Any questions? Yeah, go on, Peter.
Yeah, I have a question. First, will you share the slides afterwards?
Yeah, I think so. Yeah.
Yeah, excellent. And also this documentation you showed, do we have access to that as TSOs? Or is
Anastasia,
it
do
only
you know?
Yes, you have access, and the credentials are the same as the ones for DFT.
Okay, excellent.
So we should maybe put it in the chat.
Yes, I did yesterday, so I have answered again because someone asked again earlier.
Okay, thanks.
Okay, thank you.
Okay. So, okay, so if you don't have questions, then we can go to the EVs and then how we should do it, or shall we take a bit of break and then go to the EVs and the other topics? We don't have too many topics left, actually. We have EVs, we have the PV and the batteries, but I don't want to talk about too much about them because we don't really suggest that you use it here in the demand forecasting, but nevertheless we can talk about that a bit. And then we have two topics left: the target demand rescaling and the peak adjustment. So if you want, we have a short break. We can have a short break now and.
Yes, let's have a break now.
Okay, so 10 minutes maybe, and then.
Yes.
After 5, after 2, then we will come back. Okay. Okay. See you then.
See you.
So I think we can continue. So yeah, we talked about heat pumps, then we can talk about the electric vehicles right now. Just to be able to see a bit more. So electric vehicles, as I mentioned, this is also so-called physics aware, and also it's important that this is a deterministic relationship or calculations that are being made by DFT, and basically it's quite I know that there are many values or cells that we have to fill in, but in the end it's really a simple relationship. So for getting the daily electric vehicle load, we multiply the number of the vehicles by the average daily usage and the average daily consumption of that vehicle. And these are all of these three are user inputs. So this is just a simple multiplication. And then, of course, in order to have an hourly load, we need to have the hourly charging profile. And this is also given by the user. And for the hourly charging profile for EVs is maybe even more important to note that that ENTSO-E doesn't really want to provide like default charging profiles for each market node. So that's the reason that that in the PMDB these default profiles are flat. So we ask you to provide your own profiles if you have them, or to think about how to get them. And yeah, I know that also there are lots of possibilities for profiles up to 36. So it's a bit overwhelming, I know, but yeah, still you have the option to duplicate profiles, so it's not necessary to differentiate between all the vehicles that you provide. They can have similar profiles or the same profiles even. So, but it's important that ENTSO-E doesn't provide default profiles, even if maybe for some market nodes, as I heard, or as we were informed that previously or 2 years ago or something like that, there were some default profiles that were circulated, but for the time being, it's not really suggested or not really provided by ENTSO-E. So yeah, that's the message that I had to communicate. So yeah, basically the final electric vehicle load is just summing up all the hourly loads of the different electric vehicles based on these calculations. So this is all I wanted to like show you about the EVs. If you have any questions, feel free. I can show you the online documentation for them. It's a bit more detailed again, so you have kind of a more more detailed equation for them, how they are calculated, and you have some other aspects that they talk about. So that's it. We can go on to the next topic if you don't have any questions. So the next topic is batteries and PVs. So I'm sorry, I was a bit wrong previously. So if you want to use these and to add them to the demand here in DFT, you can do that. So it's not anymore valid what I said, that it's not suggested by ENTSO-E, because ERA study team is, if they don't like the results, they will have the chance now to like adjust the values, because the reports and the final outcomes will contain detailed information about how much these batteries affecting the load, the final total load. So if you think that for your market node it's necessary or it's relevant that you add household batteries and PVs here, then yeah, you can do that. Yeah, we can go to then this short explanation what I wrote. So it's it's important to note that batteries and PVs are computed jointly, and they are also added after the baseline forecasting. So it's also similar to EVs and heat pumps. And yeah, just to make sure it's clear, so it aims this DFT and the possibility to add these batteries here. It aims to model only residential PVs and batteries. So, and this way, the energy computed in this technological break represents how the energy is produced, stored, and used by the household. So it's important to note that what you give here is going to be a negative load. So the PV generation for these households will be either stored in the battery. So it will be stored in the battery or used by the household directly. So it won't use the grid for this amount. So that's why this is going to be kind of a negative load. How the PV computation and the batteries will takes place in the tool. So for PV computation, it's a bit different, or it's a unique kind of solution in the DFT. So it's not the same as, I don't know, it doesn't really use the PCD values for these solar technologies, but it uses the irradiance from the PCD data, and they normalize this irradiance to get a value between 0 and 1, and then they multiply this normalized irradiance value with the total PV power that is provided by the user in the PMDB. So this way, the total PV production is estimated by multiplying this total PV power and the normalized irradiance they calculate in the background. So this way, they get an hourly PV generation data. And this PV generation data is able to decrease the load, the baseline load that was previously computed, but it doesn't just directly decrease it. So because the household is expected to have batteries as well, if you provide values for them, of course. So for batteries, the developers created 3 different kind of strategies how the household uses these batteries and the generated energy that is stored in them. And I won't go into details about these different strategies here, just mention their names. So first one is a fixed profile for discharging the batteries. This fixed profile is provided by the user, so it's in the PMDB. There's also 2 other kind of automatic optimized, let's say optimized strategies. one is maximizing auto consumption, and the other is maximizing a kind of a profit. So the latter one also requires the prices of electricity, the future prices of electricity in the different hours of the days. So it even requires more input data from the user. So PVs and batteries are also included in the online documentation, and this is explained, and I hope for you these figures or plots are shown, but for me, for some reason, no. But they explain the three strategies for the battery usage. And they also explain the parameterization of these strategies, of the methodology, and they also have some advice how the user should kind of fill in the data in the PMDB file. So this is an overview of this PV and battery section in the tool. So it's possible to add household PVs and batteries to adjust their final total load. So if you feel that it's relevant for you, you can use it. But yeah, once again, coherency is really important. So I think it's really important to think about whether these PVs are, where these PVs and batteries are provided. So just to make sure that we don't double count their effect in any way. So yeah, that's it about this section. If you have any question, just feel free to ask. So if not, we can go to the two remaining parts. One is target demand rescaling and the other is this peak adjustment option. So target demand rescaling. So after we have estimated our model, a statistical model, and finalized the model which we want to use for forecasting, we can go to this forecasting section in the tool where we have to provide the target years and the climate years and also the calendar year which we want to use for our forecast. And then on the right hand side in the tool, the right hand side of the tool, we have these, we have these four options here, and target demand rescaling is one of the options here, the second one. So I will talk about right now about this option. If you select it, you use target demand rescaling, and the value that you provide as a target demand will be used by the tool, and the output will be rescaled to reflect this input, this target demand. So how it works? So actually, from a high level perspective, it's really quite a simple methodology. So rescaling is performed by applying a constant rescaling ratio to the row or the forecasted load curves. So for every hour, they will multiply the forecasted value with this rescaling ratio. And how this rescaling ratio is computed? So basically, in theory, it's just, the difference between the expected target demand and the forecasted target demand for our baseline forecast. But of course, it's just the theory, it's just the overview, it's from the high-level perspective, because we have, so the exact implementation is a bit more complex because we have many climate years, and also we have not just target demand, but we have the possibility to provide target demand for heat pumps, for the different types of heat pumps, cooling or heating target demand. So that's why it's a bit more complex than just applying a constant rescaling ratio. So how this is taken into account, this heat pump target demand? First of all, a rescaling ratio for the heat pumps is computed, and for the heat pumps we will get rescaled load curves, and then a new rescaling ratio is calculated for all the remaining part of the forecast which are subject to rescaling, and these are the batteries and the baseline demand. So after we get rescaled heat pumps, we compare, or we get what is left from the target demand to reach. So we have this remaining target demand, and then we rescale the batteries and the baseline demand in order to match this remaining target demand, and we get new kind of load curves for the batteries and the baseline demand as well. And then finally, of course, the heat pumps and these batteries and baseline demand and all the other remaining technologies which were not rescaled are added up, and this way we get this total rescaled load curve, which by construction will be in averaged by the climate years exactly the same as what the user provided as target demand. So it's also important to note that what you provide is one single value for a given target year, and the tool is or this methodology is constructed in a way that for every climate year you will get a different target demand actually, but their average in the end will be the same as what you provided as final target demand. So the average target demand, so average annual demand of the climate years will be equal to this target demand. There are many things to note here. So yeah, one thing is, yeah, so I already said that the blue part of the forecast is not rescaled. The orange part is the heat pumps, which are rescaled kind of independently, and then after that the remaining part is rescaled to match this final target demand. Usually there were, or yeah, in the past there were some problems with this remaining part. So especially the batteries. So why the batteries are rescaled, and why not the baseline demand is only rescaled? I don't know the answer for that. It was somehow specified like this in the tool, so that's why it's like that right now. So not just the baseline demand is rescaled, but also the batteries as well, and it can create confusion, and it can create confusing results in the end if there is, you know, too much gap between the remaining. So if the remaining target demand is too big, then the batteries should fill that in and not just the baseline demand. So that's why the battery part is also affected. okay, so this was just a warning, but there are some other notes which I have to mention here. That the first is that PMDB row 71 and 72 is not used actually in the tool. What's that? Okay, we can check that. I think it's yeah, and I remember. So they are kind of economic variables. Yes, this kind of GDP growth of the entire market node and the energy efficiency evolution of the base load. They are, I think, just kind of legacy values which remained here from the Trapunta era or something like that. And these are just to make sure, yeah, you are not, yeah, it's not relevant in DFT, so you don't have to fill them out. And this is just a note that these are not used, these values. The second note is that if you apply target demand rescaling, the energy growth rescaling is overridden. So you see here, I don't have a separate slide about this, but you can also apply this energy growth or decrease kind of rescaling of your forecast, and this is based on row 70. So the energy growth or decrease of the base load respect to the previous year. So you can provide percentage values here. And you can also apply this rescaling if you want, but by clicking this option. But please be aware that if you click sorry, my computer, cannot. Okay, so now it's working. So you see, you cannot even choose both of them at the same time. So this is the reason, because rescaling the target demand will override all the time energy growth decrease if it's so you cannot even select this. Okay, so it's not kind of relevant anymore, but it's good to know. And then okay, so you have the option, the possibility to provide heat pump target demands. This is in row 38 and to 40. So here you have to provide terawatt hours. But it's really, yeah, it's kind of important to know that they are only used, these values, if you click on rescaling target demand. So in this way, the target demand for heat pumps is kind of linked to the total target demand, which is in row 80. So if you would like to have target demand for heat pumps, then you have to have target demand rescaling, which is based on this row. Yeah. Okay, so these were the things I wanted to mention for target demand rescaling. Once again, the documentation in the annexes part contains maybe even more detailed explanation about these topics, where you can get to know which kind of technologies are rescaled and which are not, and then how this methodology is applied, and there are some examples for that. And also they talk about the batteries and baseline rescaling and how they get to the final total target demand. So yeah, that's it basically. Okay, if you have any question to this topic, you can feel free to ask. If not, then we can go to the peak adjustment option. So peak adjustment option is the fourth option here in the forecasting tab. So you can click on this and apply this this peak adjustment on the baseline forecasts. You also have this kind of information button in the tool, which says this option is used to redress the predicted peak values if they are under or overestimated. So yeah, this is peak adjustment, and yeah, I want to emphasize that it's not target peak rescaling. This is not the name of this feature, and there's a reason for that, because right now it's not available in the tool to have an explicit target peak for your market node for a given target year. So it's not the same as target demand, because for that we have an explicit target, and then the tool just modifies the predictions in order to meet that target demand. But for peak adjustment right now, we only have, so peak rescaling, we only have this kind of adjustment. What does it mean that we can adjust the peak? So it's really important that this peak adjustment is only applied to the base load. Now we also mention base load here. It refers to the baseline forecast, which comes out of the statistical data-driven model without adding the effects of the technologies like heat pumps and EVs and so on. So it's this kind of adjustment is only applied to this baseline forecast. It's also important to know that this is still under development, even this peak adjustment feature. So in the future, this may not be here, or this may not be like the same as it is now, but for the time being and for this data collection, I guess, this will remain the same. So you have this option here, and then the tool applies this adjustment. Okay, so I will skip the two of these slides because they are, I think, a bit technical. And first, I would like to show you this intuition, or kind of talk about the intuition, what's behind this peak adjustment. So just to understand what happens here, peak adjustment is applied on the forecast, but based on the historical load values. So that's the reason you cannot provide explicitly a peak target, because it's not peak rescaling, it's peak adjustment, and this adjustment is based on historical time series and how it is kind of estimated, or how it is done. So for this, we need this three definitions. So we need the definition of the load factor, we need the definition of a maximum expected peak, and then from that we will have an adjustment factor which will be used. So what's the load factor? That is estimated from the historical time series. The load factor is the maximum peak divided by the average daily energy, average daily power, let's say. Maybe it's not correct here. So it's kind of a relative value, and this is calculated for every day in the past for the historical time series. And And it's important that after we calculate for every day in the past this load factor, only the upper 3 percentile is kept. So we retain only this amount of values for the historical load factors, and then we average the retained values. So that's how we get this final kind of historical load factor for a given market node. So it's kind of, it only depends on the historical load time series. So it is calculated by the tool from the historical load input data. So this historical load factor is calculated. Then this historical load factor is used to calculate a maximum expected peak in the future. So we turn to the forecast and we identify the day with the maximum forecasted peak value in the forecast without adjusting anything. And we calculate its average daily energy. And then this average daily energy is multiplied by this historical load factor to get kind of this maximum expected peak, which is expected based on historical load factor and the forecast, so the average daily forecast which we got from our model. So this maximum expected peak, after we get this maximum expected peak, we use this as a benchmark. So we check whether this expected peak is below or above the exact maximum forecasted peak, which was calculated by the tool without adjusting anything. And then we can identify whether this forecasted peak is above or below this expectation. And then we can, at least the tool will apply 2 different kind of adjustments, whether it's an it's below the expected or it's over the expected peak. And you can see this adjustment here, that the reason to do this adjustment is that, you know, the peaks are going to be adjusted, but then we have to, or the tool has to retain the same energy or keep the same energy that was calculated previously. And that's why it's not just adjusting the peaks, but also we have to adjust the rest of the load curves in order to have the same amount of energy for a given year. And this is how, this is written down here, how this kind of compensation takes place in the 2 cases. So basically, this is the idea behind peak adjustment. So this algorithm is only applied to the forecast if we select this peak adjustment option. But right now in the results section, when we download the reports, especially the adjustment report or adjusted report, so we will have lots of columns, and we will have this so-called rescaled columns or variables for every kind of component of the load. And it's irrelevant whether we chose this option or not. The report will every time contain these rescaled values as well. But if we didn't select peak adjustment, these rescaled values will be the same as the original values. And if we selected this peak adjustment option, then the rescaled values will be different, and and then they will reflect kind of this historical load factor or this expected maximum peak that was computed from this historical data. Also, maybe I should not do. I will show you the one plot that is. I don't know which one I should check. So one in the results section, you have lots of some results that are shown or that are written out, and then in the end you have this graph, which I don't have right now. I don't know why. Never mind, we have it in the slides as well. So this is from this result section, and actually this plot would like to show you the expected peak and the baseline peak, whether they are, how they relate to each other. So in this way, the baseline forecasts are at one point are at the same point as the expected maximum peak. So it means that I guess the forecast is really well aligned with the historical load factor. So maybe if the user thinks like that, or is satisfied with this load factor and the result, then there is no need to rescale the peak or adjust the peak. Sorry. But of course, it's better to check in the tool, because okay, I don't have finished, because the tool has changed and there is a new version of the tool out now which contains more information, and it will help you not just see this line and the baseline forecast, but also you can compare the baseline forecast without any peak adjustment, and you will have the chance to see the peak adjusted forecast as well, and you can compare it to this maximum expected peak, and then you are kind of more easily select which one you prefer, the original one or the new one. So in this way, the tool is a bit better, because when this was the only option, it was only like you had to select the peak adjustment option. You only saw those values, and then not the original values anymore. So right now it's easier to see and follow what happened in the background, how the curves were adjusted. And here you see that on the top right you will have this button, and you can download the hourly time series for the data inside this plot. So it's also important to note that in these plots, only the daily maximum peaks are plotted, I guess. Yeah, that's one thing I should somehow, I don't know. Yeah, I'm quite sure that it's just the daily values, but you can still download the hourly values, and then you can compare them in Excel file. Okay, so actually this is what I wanted to tell you about peak adjustment. Again, peak adjustment is already in the online documentation. They tell you, they explain how it works, what are these these concepts of maximum expected peak and what happens when there is a so-called overestimated peak or an underestimated peak, how the rescaling or the adjustment, I would call it adjustment, takes place. So that's it. And actually that's it for today from my side. The novelties, yeah, we can list some novelties which happened since the last data collection or since the last, but it's not, maybe it's not relevant for you, but this online documentation and peak adjustment feature is new in the tool, relatively new. It's, I don't know, it's in the last 1 or 2 months. And then, of course, there are many developments that are being done currently. So hopefully we will have more features and easier to use features in the future. Okay, so yeah, any questions? And actually we can go to the Q&A as well. So the official Q&A.
Thank you, Andreas. So yes, let's go to the question and answers. So if anyone has a question that has not been answered yet, please feel free.
Or Anastasia, do you want to add anything which I just
No,
said?
it was all very well.
Peter, go on if you want.
Yes. Yeah, will there also come an
But we cannot
explanation
hear
of the...
I think, at least me.
Oh, can you hear me now?
No. Okay. So it's my...
You hear me now?
Yes, we can hear you.
Okay, excellent. The picked adjusted climate.
Okay, now I hear you. Sorry.
Sure.
I
Adjusted
just
climate.
started hearing. Sorry. Okay.
Yeah, I'll take it from the top. The picked adjusted climate function you can set up in the forecasting editor. Will there come an explanation of that in the documentation as well? I can't find it right now.
You mean this peak adjustment?
No, the picked PECD adjusted climate.
Yeah. I haven't talked about that. Okay, so this is a bit tricky, but not too much. So it's kind of with this option, you can select different weather variables to use for the forecast. Then that was used compared to what was used in the modeling part. So in the modeling part, there are PCD values which are in the tool already uploaded, but then there are also another version of PCD values which was created back, I don't know, in 2021 maybe, and they were kind of adjusted for climate change. But I think they are not like an official PCD version, something like that. So they were maybe created for specific purposes. But this is also included in the tool, and you select to use them for forecasting. But it's not really clear how they differ from the original values. So I don't have any kind of suggestion whether you should use it or not. We didn't really explore this, and I think it won't be that relevant in the future, because in the future we will have a more official way to incorporate BCD values, BCD 4.1 or 4 will come to the DFT soon, and then it will be more transparent what's behind these forecasts. So I don't know, Anastasia, what do you think? What you should say about this option?
So indeed, the PCD adjustment is not available yet in the documentation, in the online documentation. However, in the one that we are going to share with you, the PDF version, you will have some details. But in the instructions that we will share with you during the launch of the data collection, you will have more information about whether to use it or not. Because it also depends on the new PCD version that we are going to use for the new data collection. So just for your information for now, we are going to use PCD 4.1 probably, and more information and guidelines will follow about that.
Yeah, so also this option will be explained a bit more.
Yes,
because the background data will probably change. So yeah,
it's just that it's still under construction, but we are still waiting for some data, and this is why we're not 100% prepared, but we are going to use this new version in 2 weeks.
Okay, so but it is using some kind of adjusted picked profiles, because we have used it for our profiles we have made. We have ticked off this picked adjusted, but it is using some kind of adjusted climate profiles here.
So I didn't really understand the last sentence you made. So you selected them previously, and
yeah. So my question is just that we are using some adjusted climate profiles if we use this picked adjusted. Okay.
Yeah, but the problem is that right now it's not really transparent even for us. What's the difference between the original and this adjusted one? But soon it will be more transparent and clear what is behind this option and which PCD values are there, and that's why we don't really include it here. And previously we suggested to use it, always tick it, but yeah, right now we will have communication about that. Thank you for the question.
Any other question?
Hi. Yeah, my question is regarding partial correlation in the beginning of the modeling. That I tried to simulate two kinds of models at once. Everything same except for the splines. One model I did with say lower number of splines for everything and higher just to see, how the results are. And yeah, like expected with higher splines, there's more granularity. So it's more, let's say, wobbly data. But the thing is, there's no feedback that I understand. Like, what should I go forward with here? Because if the splines are low, yes, it's more close to a linear model. Whereas if they're high, then it's very wavy. But is there a reference or something that I can check back to? Okay, this is somewhat adjust. I know it's trial and error most of all, but still there has to be like a sense of reference as to what I can trace back to.
Yeah, good question. Actually, I don't have a good answer for that. So I think it's a bit subjective. So, and also it's specific to the market node and also the variables that you look at. So I don't know. So short answer, no benchmark, no reference, like strict reference. It's kind of really just what you see, whether you see a relationship, whether it's sensible or not for you. It's So it's, yeah, I don't have a really good answer for that. And I think, I don't know, comparing to 4 splines and 5 splines, comparing them, maybe they don't have a real difference. So I think the real difference comes at a bigger difference between the number of splines. So that's also something which you can try, and maybe the exact number is not that important. So 4 or 5 is not that important, but to be, I don't know, under 10 is more important, maybe, because then you see that the function starts, I don't know, getting more wigglier. So yeah, short answer, no benchmark, no reference from our side.
I see. Okay, I tried with everything 5 and then everything 10.
Ah,
Yeah, so just because I wanted to keep like everything similar and see how what's the difference. So I think I have to, yeah, find something in between because 10 is extremely wavy, whereas 5 is very close to linear. So
okay.
yeah,
Mhm.
the results are very different for like with lower splines, the graph is actually tending upwards, but with more splines, the end part is really
And
dipping
it's
down. So
coming down, yeah. So that's
yeah.
also maybe if you expect, I don't know, for temperature, if you expect in the future more, or in the PCD, you know that there are more higher values than in the past. So the tool has to extrapolate. Then the end of the function of this relationship is really what matters. And if you want that to be like modest, then yeah, you maybe don't want it to explode in the end. So yeah, these are kind of aspects which are kind of not easy to have a good advice on, but yeah, with experience, with some trials, yeah, you can do something. But I understand that it's a bit it can be a bit tricky.
Yeah, in my experience, I think wind speed was the most variable parameter because I think it has the highest variability within the day as well. Whereas temperature and population weighted temperature, everything that was still okay. There were some trends followed between lower and higher splines, but wind speed was the most variable. So I think there the splines can be, yeah, seen.
Yeah, I also think that this is a reason because so the reason for this may be one of the reasons is that so for wind speed there is not a kind of a clear relationship. It's really the, the parameters are not that easy to estimate, and there is much uncertainty in those parameters. So that's why it can be a bit more uncertain or wigglier. But then this also means that wind speed is not that of an important variable. So so maybe it's not that big of a problem in the end. But I also, for this, I don't have a kind of objective evidence, but I'm just having some kind of experience with the tool and how it worked for us, and we saw the same. So wind speed is not a really important variable. It is important in some periods, and that's why it's not really the most important thing. What I look at actually when I do the modeling. Yeah.
Yeah, so in essence, there is no way to look at the data as such. Like you just get the results as to, okay, this is how the relationship is, like the regression goes, but you cannot kind of visually look at the scattered points. That's where my question was coming from.
Yeah. It's missing. Yeah, I know.
Mm,
So you can
okay.
only just one by one check the daily average of all those variables and not their relationship.
Okay.
Yeah.
Yeah. There was also a reply in the chat just now relating to what we're talking about, so you can also read that. But thanks for the answers. Yeah. Thanks.
Yeah. Welcome. Yeah, so the more flexible the model will be, it will be better for the training sample. Yeah. But then for forecasting, maybe it's not that useful to have many splines and the most number of splines possible. But the tool tries to assess the forecasting performance with these, test periods. They calculate these metrics, RMSE, and so on for the test period as well, which is not seen by the model for the first time or when you select the model itself. And also these cross-validated metrics are also kind of would like to catch or to assess this forecasting performance. Until you have some questions, maybe Anastasia, are you here? So maybe the timeline
Yes.
we can show again and talk about it a bit more.
So the timeline for the data collection, you mean?
Yeah, maybe. What is the next for?
Okay, so the plan is
for us?
to start the data collection on the 20th of November. There will be 3 workshop weeks, and each week that you have registered for, you will need to run the tool during that week and create the time series. I understand that some TSO members have registered for more than 1 workshop week because they anticipate that 1 will not be enough, and we understand that. We are going to start collecting. We are going to send you an email with the templates and what we need to collect before the 20th, of course. And in order to run some quality checks in the load files, at least, we will need the load files to be sent before the 20th for the ones that are registered for the first week. And then we will run the quality checks for the load file. And so after that, we will need to upload in the database the load files and the load files only, actually. And after that, you will be able to start a project in DFT and run the tool during the whole week. Or well, if there are delays, of course, we are going to support you with that. And in any case, during the workshop weeks, these are actually a kind of hotline support where you can just join the call, and we will be there in order to answer questions and help you with the creation of the time series. So the call will be open for approximately 8 hours. If we are not available, we are going to send you a message or have an automatic message, and then arrange a time slot that we can both parts be available. Yeah, are there any questions? For the ones that already participated in the previous training, this is the same way that we did it last time for the SACs. Yeah. And after the collection of the data, after the 3rd week of the workshops, in the end of December, we will run the quality checks and distribute to you the final reports from the quality checks of the outputs. And then if both of the parts, like ENTSO-E and TSOs, think that the time series are fine, we are going to send them to the study teams. Otherwise, we'll be in communication with you to rerun probably the DFT. Any questions? Okay, I will take this as a no. Otherwise, you will also be able to send us an email if you need something. So yeah, our instructions will follow by email, and after this meeting, you will have also the recordings and the presentations of the trainings. Thank you all. Have a good rest of the week and weekend.
Thank you. You too.
Yeah, thank you. Bye bye.
You.